Hello all. I'm just quickly going to go over some things for the project as per the request of some of you. So what we need to do is basically add the required components and solve the hazard problem if forwarding is needed. So we need to solve the data hazards by creating some additional forwarding unit. These are the instructions which we're going to be using. And as you can see, these instructions don't really require any stalls happening to them, because if we have a proper forwarding unit in place, we can make sure there are no stalls required. And that is, in the end, our purpose, to solve as many hazards as we can with the minimum number of stalls. So as you can see over here, we have a bunch of R-type instructions. And before I get into that, let me just show you what you have to implement. So this is what you have to implement, figure 4 of the project PDF. Now I understand that may seem too confusing because it is beyond the 10%. It was not provided to you so that you may think about it, but this is what you have to implement for just the 10%, which is the project. You need to have 2 new multiplexers, namely the forwarding A and forwarding B, and you need to make some updates to the control unit. So if you can see over here, we have a dependency from the add instruction and the rest of the instructions for the register 3. We know that 3 is the destination register, or RD, for the add instruction, and is one of the source registers, RT, in the subtraction instruction. So there is a dependency on that. And we can perform some kind of forwarding, namely ALU to ALU forwarding for this instruction, so that we can pass the value in without any stalls. And if you remember, ALU to ALU forwarding for 2 R-type instructions does not require any stalls. So how do we do that? These 2 multiplexers help us perform that. Now, if you remember, the destination register comes from this multiplexer over here from the first lab, which did the pipelining. This destination register, if you see, moves to the next stage, is also being passed back to the control unit. And as well as RS and RT are taken as inputs into the control unit. Maybe there is a way, if we make some kind of comparison between this RS and RT with ERN, saying, oh, okay, if either of these equal to ERN, there could be some kind of dependency, and I need to perform some kind of forwarding, whether it be ALU to ALU forwarding, or memory to ALU forwarding, or memory to memory forwarding. We don't know. That's based on the type of instructions. In our case, we're dealing with R-type instructions. So it's mainly going to be ALU to ALU forwarding or memory to ALU forwarding. So let's look at the first one. In the first one, we know that RT is equal to ERN. So in that case, we need to do an ALU to ALU forwarding. So that's and as you can see over here, the 4 cases are, because as you can see, the 4 cases over here, if you just backtrack these wires, I've just written down what is exactly these backtrack wires. When you want it such that when it's 0, 0, there are no hazards, that means I just do the normal thing I would do, which is passing in QA. And if it was for forwarding B, you just do QB. Now here, if I'm 0, 1, I would pass in R from the ALU. And that's what happens when, in our case, such that, because R is happening such that RT is ERN. But also just keep in mind, RS, whenever RS is equal to something, or you do some changes with these, make sure you update this multiplexer. And whenever it's RT, you do forward B. So ALU to ALU forwarding, basically that it's coming back. The ALU output comes back, and then you can use that ALU output again to perform another ALU operation known as the subtraction operation in our case. And for the 1, 0 case, it's MR, this output, this output being coming back to the ALU. And the case of do is when you have some kind of a load word dependency, and you just pass that from the data memory. So these are the 4 cases for forward A, and you'd have the same 4 cases for forward B, except with QB over here. And the selected bits obviously are forward A and forward B. These selected bits values are decided by the comparisons you make between RSRT and these other inputs over here. Do not worry too much about WPCR, that is just a write enable. And since in our case, we don't have any stalls, we don't need to worry too much about it. It's just a simple NOT gate over here. That's mainly because if we write on the positive edge of the clock over here, we can read the value of 3 at the negative edge of the clock, and that will help us reduce or remove a stall, which otherwise I would have had to place for this XOR instruction. And then this helps us remove any kind of stalls for this at all. There's no forwarding involved in the XOR in the end, because by the time I reach the 5th clock cycle, I've already updated the value of 3 in my reg file. So another small update to the reg file, you just need to initialize the 11 first words. Before, if you remember, we just used a for loop to initialize everything to 0. This is the reg file, not the data memory. Keep that in mind. Also, just if you haven't already, make updates to the ALU to handle the add, sub, or XOR and AND, and also update the instruction memory. With these instructions, you can start from 100 again, so 100, 104, 108, 112, 116. Those are going to be a program counters respectively. So that's all you need to do for the project, which is the 10%. You just need to add the two multiplexers, make updates to the control unit, and some minor updates to the reg file, ALU, and instruction memory, respectively. All right, moving on next to the additional extracurricular part of the lab. If you implement this, you get additional 5% to your total grade. So for that, you would obviously have to do the project, which is the two multiplexers forwarding over here. There's the comparator when you have some kind of a branch, when you have some kind of BEQ or some kind of JN type instruction like that. Sorry, I type. And also, if you have some J type instructions over here, where you have to find the jump address, the branch to address, you need to make some comparisons using the shifting and some adding, and then pass it to the multiplexer. And it's not always the case you just do PC plus 4, especially when you have a J type or you have a jump and link. You would need to select the appropriate one, which again comes from the PC source, which is you should manually hardcode in the control unit. You have a small forwarding unit over here from the destination register, which kind of does the same things done for the project, as well as another multiplexer just selects between the output of that and the sign extender. And those are some of the specific cases. Also, please keep in mind that these are the instructions to use for the additional 5%. So if you're doing the additional 5%, follow these instructions. You don't need to copy paste this as the instruction memory. You can just use these specific instructions starting from 0, 4, 8, and so on, and as well as for the data memory. And please read all of this information, as this is it'll help you debug and come up with ideas for the code. That's it. So this whole thing is 5%. This is the breakdown for all the types of instructions to help you figure out all the cases. And this should be some kind of a test waveform you should have. So this is all for the additional 5%. If you want to just implement the project, it's just these two multiplexers, updates the control unit. And I think this is reasonably doable. And also, we just want you to write a small paragraph explaining what you did if you're doing the project alone. So in that, you can just mention the two multiplexers you're dealing with, the updates to the control unit, some comparisons you made, and how you decided the respective forward A and forward B bits accordingly. And that should be it. Stick to the format. And if you have any further questions, please let me know. Thank you.